Hello dear friends, welcome to my channels. Today's discussions is hydrogen atom, quantum mechanics, quantum theory of the hydrogen atom. So friends, we need to discuss Balmer series. So Balmer and the hydrogen spectrums. Okay. So 1885, Johann Balmer, a Swiss school teacher, empirically deduced a formula which predicted the wavelength of emission of hydrogen, lambda, in Armstrong is equal to 3645.6 into n square divided by n square minus 4. For n equals to 3456, predicts the wavelengths of the four visible emission lines from hydrogen, which are called Balmer series, implies that there is some underlying order in the atom that results in the deceptively simple equation. The Bohr atom. Niels Bohr uses quantum theory to explain the origin of the line spectrum of hydrogen. The electron in a hydrogen atom can exist only in discrete orbits. The orbits are circular paths about the nucleus at varying radii. Each orbit corresponds to a particular energy. Each orbit corresponds to a particular energy. Orbit energies increase with increasing radii. The lowest energy orbit is called ground state. After absorbing energy, the electron jumps to higher energy orbit, an excited state. When the E drops down to lower energy orbit, the energy lost can be given off as a quantum of light. The energy of photon emitted is equal to the difference in energies of the two orbits involved. More Bohr. Mathematically, Bohr equated the two forces acting on the orbit electrons, Coulombic attractions and centrifugal accelerations. So Coulombic attractions is J divided by 4 pi epsilon 0 E square by R square. Okay, this is the formula of the Coulomb. This J by 4 pi epsilon 0, this is called also K in terms, means constant term, and equals to mv square divided by R. This value is 9.9 into 10 to the power 9. Okay, no problem. Rearranging and making the wild assumptions. MVR is equal to NH divided by 2 pi, and E minus angular momentum can have certain quantified values in whole multiples of H divided by 2 pi. Hydrogen energy levels. Based on the model, Bohr arrived at a simple equations to calculate the electron energy levels in hydrogen. And En equals to minus RH divided by 1 by n squared. For n equals to 1, 2, 3, 4. Where RH equal to 2.179 into 10 to the power minus 18 joule. The Rydberg constant n is the principal quantum number. Radii can be calculated to Rn is equal to n square A0. A0 is equal to Bohr radius. Transitions A0 is equal to 0.529 Armstrong. Transitions between energy levels. Now the energy change associated with transitions between electron energy levels can be quantified del E is equal to E final minus E initial is equal to H nu. Okay, final energy minus initial energy, that is the changing energy, equals to H nu. H is equal to Planck constant and nu is equal to wavelength. And H nu is equal to RH minus n square F and minus into minus RH divided by n square I. N square I means initial and n square F means final. So collecting terms, RH by H square H divided by into 1 by Ni square plus 1 by Nf square is equal to nu. Nu means, and Bohr versus Blamar. With some rearranging, the Blamar equation looks like this: 3.29 into 10 to the power 15 per second, 1 by 2 square minus 1 by n square. And this is the equation we just derived, but with Nf is equal to final n fixed at a value of 2. So the Bohr model also accurately predicts the frequencies of the Blamar series emission lines. But it also predicts other emission lines for Nf is equal to 1, 3, 4, etc. Hydrogen's energy level diagram. When Nf is equal to 2, then Blamar series is visible emission, and when Nf is equal to 3, this is the Paschen series, and that is infrared emission. So friends, this is the diagram. This is the principle of quantum number, n equals to 2, and this is the spectroscopy. Sample calculation, calculate the wavelength at which the least energetic emission spectral line of a Lyman series is observed. Lyman, when Nf is equal to 1. Lowest energy transitions will be 2 to tends to 1. So RH is equal to 1 by T square divided by 1 by 1 square. And Rydberg constant, this is the Rydberg constant, 2.179 into 10 to the power minus 18 joule, 1 by 4 minus 1. And I get the losing energy. So converting wavelength, Hc is equal to del E. So del E I get an Hc value is equal to 6.626 into 10 to the power minus 34 joule per second. That is the Planck constant value. And velocity of the light is equal to 3 into 10 to the power 8 meter per second, and divided by losing energy 1.63425 into 10 to the power minus 18 joule. So when it is divided, then I get 121.5 nanometer. Nanometer means 10 to the power minus 9. So this is the 10 to the power minus 9 meter. That is called nanometer. Wave properties of matter. De Broglie, if EMR waves can act like particles, why not treat matter like a wave? This is the based on hypothesis. Characteristics wavelength length of the object is lambda, and h is the Planck constant, mv is the momentum of object. Result: macroscopic things have wavelengths that are incredibly teeny, 10 to the power minus 30 meter, and so subatomic sized things have wavelengths that are of the same order as the physical size. Armstrong for an electron. The uncertainty principle. German physicist Werner Heisenberg. There are limits to which we can know both the momentum and the location of any object. Del P into del X greater than equals to h divided by 4 pi. Quantitatively, so the better we know the position of an object, the worse we know the velocity p equals to mv of the object. Not an issue of the macroscopic world, but the limitation is profound for objects like electrons. Quantum mechanics. Erwin Schrodinger describes electrons in an atom as having both wave and particles properties. Erwin Schrodinger describes electron in an atom as having both wave and particle properties. The Schrodinger wave equations results. Solution to the wave equation are called wave functions. For hydrogen, get the same electron energies as Bohr did. The square of the wave function is equal to psi square gives the probability density for an electron in a specified energy state. So Schrodinger have means particle has atom has two type. Must remember this property, wave and particle properties. Okay, so electrons in an atom has two property, wave and particle properties. So probability density, this is the probability densities define what are called orbitals. Orbitals and quantum number. Each solutions to the wave equation can be uniquely specified by three quantum number. The principal quantum number n can have integer values 2, 1, 2, 3, 4, etc. and corresponds to the principal energy level, same as the quantum number in Bohr model defines the electron shell. Azimuthal quantum number can have integer values of 0 to n-1. Each value of n defines the orbital shape, and value of L determines the letter used to specify the orbital shape. L equals to 0, 1, 2, 3 SPDF orbitals defines the sharp shape. Lowest energy orbitals for the hydrogen atom. More Qn and orbitals. So the magnetic quantum number ml can have integer values of L and minus L, describes the orientations of the orbital in space. For some examples, n equals to 1, one of the values of L possible O, and one of the only one values of ml possible O, first orbital, and L equals to 1 to 0, 0 to 1 S and P orbitals. For L equals to 1, ml equals to 1, 0 and minus 1, 2px, 2py, 2pz orbitals. Ammonia fountain demo. One of the example, ammonium fountain. The reaction NH3 is equal to NH3 gas is equal to NH3 aqueous, where the minus energy loss 46.11 kilojoule per mole and 80.20 kilojoule per mole. So energy changing is equal to 80.20 and 46.11, 34 minus 34.18 kilojoule, and N is equal to PV divided by RT. So 8.7 into 10 to the power minus 2 mole. This is the calculations, friends. PV is equal to 1 atmosphere, liter, V is equal to 2 liter, and this is the R value and T value. 298.15 K. This is my temperature and this is my R value. So PV work is equal to del nRT. So I get 200 joule. More Qn and orbital. Magnetic quantum number is equal to can have integers values from 1 and minus 1, describes the orientations of the orbital in space. So some examples, n equals to 1, only one value of L possible 0 and only one value ml possible 0, first orbital. Second orbital 0, L is equal to 0 and 1, S and P orbitals, ml is equal to 1, 0 and minus 1. This is a 2px, 2py, 2pz orbital. And L equals to 0, 1, 2, L equals to 2, ml is equal to 2, 1, 0, minus 1, minus 2. 5 3D orbitals. This is a diagram, orbital energies. For hydrogen, energies vary with n, same result as with Bohr. En is equal to E to the power 4 me z square. So friends, we see that energy En equals to minus e to the power 4 mez square divided by 8 epsilon 0. Epsilon 0 is equal to absolute permittivity h square divided by n square z square is equal to minus rh z square divided by n square. So friends, this is the orbital energies, and you see the diagram. Okay, when n equals to 1, 2, 3, 1s, 2s, 2s, 2p, 2p, and 3d. Also applies to other one electron systems. This is my electron system 1s, 2s, and 3s. N equals to 3, L equals to 0, N equals to 2, L equals to 0, N equals to 1, L equals to 0. And this is the phi 1 square, phi squared, and node and nodes. So friends, orbital shapes s orbitals. All s orbitals are spherical but have different radial probabilities distributions. S orbitals have n-1 radial nodes. As n increases, so does the orbital size. Orbital shapes p orbitals. P orbitals are dumbbell shaped. Subscripts indicate primary orientation axis, nodal plane at nucleus. As n increases, the size of p orbitals increases. This is the diagram. Px, Py, this is the subscript you see. Orbital shapes d orbitals, 3-4 leaf cover shapes in 3 planes oriented between the axes. One dumbbell shape with a duff knot in xy plane, and one 4-leaf clover shape in xy plane oriented along the axis. And this is the diagram. The Schrodinger equation in spherical coordinates. So friends, here is some story that there are many good reasons to address the hydrogen atom beyond the historical significance. Though hydrogen spectra motivated much of the early quantum theory research involving the hydrogen remains at the cutting edge of science and technology. For instance, transitions in hydrogen are being used 1997-1998 to examine constancy. The constancy of the fine structure constant over the cosmological time scale. From the viewpoint of pedagogy, the hydrogen atom merges many of the concepts and techniques previously developed into one package. It is a particle in a box and with spherical soft walls. Finally, the hydrogen atom is one of the precious few realistic system which can actually be solved analytically. The Schrodinger equation in spherical coordinate. So that separated time to arrive the time independent Schrodinger equation is time independent Schrodinger equation H E I bracket Kate bra and Kate functions. So friends, so eigenvalues EI are where EI is eigenvalues and Kate is the energy eigenstates. And we developed a one-dimensional position space representations at the time-independent Schrodinger equation, changing the notation such that EI tends to E and EI, Kate EI tends to sigma. So we get that h square h bar square 2m divided by del square plus v is psi is equal to e psi, and del square is a Laplacian operator, where del square is Laplacian operator. Using the Laplacian in spherical coordinate, the Schrodinger equation becomes, this is the Schrodinger equations in spherical coordinate. And complete set of commutating observable for hydrogen. This is the equations of the complete hydrogens. And del square is equal to Laplacian can be written as del square is equal to Laplacian can be written del square del r square 2 by r del r l square divided by r square is h bar square. So the Schrodinger equation becomes h bar square divided 2m divided by e psi, and according to the spherical symmetry which we will have become, a Coulomb potential will be used for VR. Coulomb potential, we have capital VR is the Coulomb potential. Without radial variable, we have a complete set of commutating observable angular momentum operators. L square is equal to capital L square is equal to Lj and Lj momentum operators. So the radial variable, we need the minimum of one more operator. If that operator commutes with both L square and Lz, the total energy operators, the Hamiltonian, may be reasonable candidate. What is the Hamiltonian here? It is the group of the terms within the square brackets. And if you have difficulty visualizing that, in fact h is equal to L square and Lz equals to 0. So the complete set commutating observable for the hydrogen atom is h, L square and Lz. We have the eigenvalues and eigen vector equations, because the time independent Schrodinger equation is the eigenvalue eigenvector equations for the Hamiltonian operator. Then the eigenvalue and eigenvectors equations are h psi is equal to en psi, and L square psi is equal to L plus 1 into h bar square psi, and Lz is equal to mh bar psi. So where we subscripted the energy eigenvalue with an n, because the symbol conventionally used in energy quantum number per particles in a box SHO. Then the solution to the problem in the eigenstate which satisfies all three and denoted NLM kit. In abstract Hilbert space, the representations in position space is spherical coordinate is r theta gamma phi NLM is equal to this. Thanks for watching. We will create a lot of video based on hydrogen atom. So thanks for watching. I hope I can give some idea about this hydrogen atom in this video.